In this video, we will begin reviewing for the final. So we're going to focus the videos for today's lecture on the material from after midterm 2. So this is stuff from sections 14.1 up to 14.8. Okay, so our goals for today's lecture videos are to do some practice problems from chapter 14 to prep for the final. Okay, so I'm just going to combine this into our first topic of review. So I want to review directional derivatives and gradients a bit. Okay, so let's begin by just reviewing some properties of each of these. So with the gradient, let's remember the formula for the gradient is, so if f was a function of 3 variables, say, so if f, let's say f was a function of x and y and z, then when we take the gradient, that we'll get the partial with respect to x, that's the first component of a vector, and the partial with respect to y is the next component, and then the partial with respect to z would be the next component. If our function only had 2 variables, the gradient vector would just have 2 components, and so on. It corresponds. However many variables the function has, that's how many components the gradient would have. And the directional derivative, the formula for that is, so if I write du, so u is the unit vector that I'm taking the derivative in the direction of my function f. The formula for this is, it's the gradient of f dotted with that unit vector u that we're taking the derivative in the direction of. Okay. All right, so I'm going to put a bullet point next to this, and I'll put a bullet point next to this. And I'm going to write down a few more properties now. So these are the formulas for each of them. Let's write down some properties. So one property about the gradient is that the gradient points in the direction of greatest increase. It points in the direction that the function f would increase the most. So another property of the gradient is, if we had the gradient of a function, and it was a function of 2 variables, we can draw level curves here, and the gradient is normal, or perpendicular, it's normal to the level curve that x, y, whatever point we're looking at, is on. Right, so that's a property that we've seen that the gradient has. And if I went one dimension up and I had a function of 3 variables, so if I had a function of 3 variables and took its gradient, well then we'd be talking about level surfaces, and this gradient would be normal to the level surface that the point x, y, z is on. Okay. And what that would mean is that the gradient vector here, if we're talking about the gradient for a function of 3 variables, this equals, it's going to be a normal vector to the tangent plane. So in this case, we have a level surface, and the gradient vector is normal to that surface. And that would mean that it's also a normal vector to the tangent plane. So the tangent plane to our level surface, which is f of x comma y comma z equals c, where c is some constant. All right, so those are some properties of the gradient. Let's write down some properties of the directional derivative. Okay, so the first one is that the largest this directional derivative gets, so I'll say the largest directional derivative occurs when the direction vector u points in the same direction as the gradient. So that matches up with this first property of the gradient that we wrote. We said that the gradient points in the direction of greatest increase. So that's basically what this is saying. It's saying that if you want to find the biggest possible directional derivative, take it in the direction that the gradient is pointing in. Okay, and then on the flip side, the smallest directional derivative occurs when u points in the opposite direction as the gradient of f. Or in other words, it's pointing in the same direction as the negative gradient of f. Okay, so yet another way to say that is, if you want to know what direction is the direction of greatest decrease, it's negative gradient of f, or the opposite of the gradient of f. Okay, so we did a bit of a review. Let's do a practice problem now. So this is from the final practice problems, part 1. So part 1 is the chapter 14 practice problems, and it's problem number 2. Okay, so this problem talks about in x, y, z space, we have this temperature function, and it says that we are at the point 2, 0, 1, and at that point the temperature is 3 degrees. And we could actually verify that by just plugging in 2, 0, 1. And if we did that, we'd get 4 times x, which is 2, times y, which is 0, plus 3 times z squared, so 3 times 1 squared. And that's just 0 plus 3, which is 3. So that's how they got to 3 degrees. Okay, so that's pretty cold. All right, so in part A, in what direction should you go from that point 2, 0, 1 in order to warm up the fastest? Okay, so what I want you to do is first pause the video for about, let's say 4 minutes, maybe even 4 to 5 minutes to try this problem. If you get done with part A, move on to part B and so on. But 4, 3, 2, 1, pause the video. Pause the video and try this for about 4 minutes. Today, especially on these review days, it's really important to seize this time to try these problems on your own before we talk about them together. Because on the final exam, ultimately what I'm going to be doing is I'm going to be assessing your ability to apply concepts that you've learned to tackle new problems. So because that's what I'm assessing, you want to practice that skill. You want to practice tackling new problems. So it's really important to seize this time to try these problems on your own first to gauge how well can I accomplish that skill? How well can I actually tackle problems on my own first? Alright, so hopefully you've paused the video and tried this for about 4 to 5 minutes. So let's start to talk about it together. But if you haven't paused the video, again, really encourage you to do that. Okay, so let's talk about part A. So what direction should we go if we want to warm up the fastest? So in other words, we want to know when the temperature increases fastest. So temperature increases fastest in the same direction as the gradient. So as the gradient of t. So let's find the gradient of t. So it's a function of 3 variables. So we'll get a vector where the components are tx, ty, and tz, so 3 partial derivatives. Okay, so the partial derivative with respect to x, so for the first term we'll get a 4y. For the next term, 3z squared, we'll get 0 because there's no x's in it. Okay, and then for the partial with respect to y, we will get 4x. And the partial with respect to z, we'll get 6z. So that's our gradient. Now let's plug in our point. So we want the gradient at the point 2, 0, 1, because that's where we are at. So plugging that in, we get 4 times the y value, 0, times 4 times the x value, 2, plus 6 times the z value, which is 1. All right, and simplifying this, we get 0, 8, 6. So that's my gradient vector. That's the direction that we should travel in if we want our function to increase the most. Okay, so that's actually the answer to part A. What's the direction? Well, it's the direction that this vector is pointing in. All right, so let's try part B now. Part B is asking, well, what's the directional derivative? What is the directional derivative in that direction? So the direction we got in part A, at that point, at the point 2, 0, 1. So if you didn't get a chance to try part B before when you paused the video, pause it this time just for 2 minutes to try this question. It's probably not going to be enough time to finish it, but I mostly care about, can you figure out what the key ideas are and how to begin? 4, 3, 2, 1, pause the video. Pause the video and really try this for 2 minutes. So again, just like I mentioned before, for the first pause, really believe that the time that you put in to try these questions on your own first is going to help. Even when you don't finish the problem, believe that that work that you put in is going to be helpful in the long run in your prep. All right, so let's talk about it together. So what is that directional derivative? Okay, so I actually want to talk about how to do this in 2 ways. So first, I'll call this method 1. So if we use our formula for the directional derivative, du, and our function is t, we get the gradient of t dotted with the vector u. Okay, so u is a normal vector in the direction that we're taking this directional derivative in. Okay, so we know what direction it's got to be in. It's got to be this direction. But u needs to be a normal vector. So we need to normalize the vector 0, 8, 6. Remember, normalize just means turn it into a unit vector. Okay, so u is going to be, the way we do that is you do 1 over the length of the vector, 0, 8, 6, and then multiply it by the vector. So multiply it by 0, 8, 6. So let's simplify. So using our formula for length, this is 1 over the square root of 0 squared plus 8 squared plus 6 squared times that vector, 0, 8, 6. So the denominator of this fraction ends up being 10. So we get 1/10 times 0, 8, 6. And now we can distribute in the 1/10, and that'll give us 0, 4/5, 3/5. So that's u. That's this unit vector. Okay, so now let's dot these two things. So our gradient was 4y, 4x, 6z. I need to dot that with u, and u I now know is 0, 4/5, 3/5. So dotting these, we get 0 plus 16 over 5x plus 18 over 5z. All right, so we want to know this directional derivative at the point 2, 0, 1. So let's plug this point in. All right, so if we do that, we get 16 over 5 times x, so times 2, and then plus 18 over 5 times z, which is 1. Okay, so overall, we end up getting 32 over 5 plus 18 over 5. That's 50 over 5. That's 10. And the units here, so the units of temperature are degrees. And the units that I divide by are just the units of direction, which aren't given. So I'll just say per unit. Ooh, whoops. Screen got shifted there. Okay, degrees per unit. All right, so that is my directional derivative. So I mentioned that we would do this in two ways. So let's talk about the second method. So it's useful to see multiple methods in one because problems can be done in more than one way, but also in terms of a timed test like a final, being able to know there's multiple ways to do this, but what might be the most efficient way that would save me time. Okay, so I'm going to start off method 2 in the same way. My directional derivative is the gradient of t dotted with u. But the way I'll approach it now is to say that, okay, I know what direction I need to go in. I know that this needs to be in the same direction as the gradient of t. So the two vectors that I'm dotting are in the exact same direction, which means the angle between them is 0. So if I drew out my gradient of t vector, let's say it was something like this, and then I drew out my unit vector, well, I'm saying the unit vector is in the same direction as the gradient of t. I'll call this u. So that means theta, the angle between them, is 0. Okay, and why that's useful to know is we had this formula for the dot product involving cosine of theta. So the dot product equals the length of the first vector times the length of the second one times cosine of that angle. Okay, so we got the length of the gradient. The length of u is 1, because that's a unit vector. And then we have cosine of 0. But cosine of 0 is 1. So overall, we just have the length of the gradient. Okay, so at this point, let's plug in the point that we're doing this at. So the directional derivative at the point 2, 0, 1, we now know is equal to the length of the gradient at that point, 2, 0, 1. All right, so let's plug in this point into the gradient. All right, so that gives us 4 times y. Whoops, sorry. Start my vector. And then times 4 times x. And then the next component was 6 times z. So that was the gradient when we plug in our point. But I need to take its length. So this is the length of the vector. If I simplify it, it's 0, 8, 6. And we actually took the length of this vector in method 1. We got that it was 10. And that's my answer. It's the same thing I got in method 1. And the units of this were degrees per unit. Okay, so we have these two methods for tackling this question. So part C of this problem, I'm going to leave for you to try. All right, so in the next video, we are going to review optimization.